It's great. Okay.
Oh, I think
So we'll wait for a couple of minutes before people start. Uh, I think it'll take a couple of minutes for people to join in. Let the number go up. Go up, please. Let's give it a minute.
sure thing.
Okay. I think that's 10 more seconds.
All right. Give me just enough time to fix it up.
Oh, nice. Okay. Okay, let's get started. Good afternoon, folks. Uh, this is Vijay, your host, and joining me is Reuven. A little bit about the topic that you're going to talk about. It's generators, coroutines, and nanoservices. I'm assuming most of you know what those three terms are. Maybe we'll learn a little bit about what nanoservices are today. But before we jump in, let's introduce Reuven. So Reuven is actually a well-known teacher of Python and data science around the world. He is one of the creators of the first 100 websites in the world after graduating MIT's computer science department. And some of his clients include Apple, PayPal, Cisco, and many more. So thanks, Reuven, for deciding to uh, share your knowledge on this topic. I'm excited about nanoservices. So let's get started.
Excellent, excellent. Thank you so much, Vijay. Hi, everyone. It is great to have you here. I actually was in Hyderabad last year doing some corporate training, and I was supposed to go back this year. Strangely, the pandemic made that impossible. But there's always hope for next year, and then I can meet hopefully a bunch of you in person as well. So this talk, as you see, as Vijay said, is called Generators, Coroutines, and Nanoservices. And just a few words about myself. As Vijay said, like I teach Python. I teach Python at companies all around the world. I have my book. I should have the book right here. Python Workout that Manning produced. I have a weekly newsletter about Python called Better Developers, currently read by about 20,000 people each week. Um, and I'm going to talk about generators, coroutines, and nanoservices. But the most important thing that you should realize is this is not an async IO talk. And I know that might be a little surprising. I'm going to try to wrap it all together in the end and sort of explain to you how it might sort of kind of be a bit of an async IO talk. But what I want to start talking to you about is let's start off with what I call the dumbest function in the world, right? So it's just going to be def myfunc, return one, return two, return three. Now, what happens when I run this function and then I wrap it around with print? What's going to happen? It is not a surprise, I assume, to many of you that it's going to print one, right? Because it's going to print one and then it returns, and that's the end of that. Well, that's because, of course, return says not just I want to return this value, but I want the function to stop right here. And the fact is that if you run it through, say, pylint, which is a code checker for your code, it'll say, hey, dummy, you've got two lines in here that you can't get to. These are unreachable lines of code. And even if you tried in the byte compiler in Python, when it turns your code, your function, into that low-level stuff, it actually won't even look at those last two lines at all. It's smart enough to know. And the byte compiler in Python is not the smartest thing in the world, but it's smart enough to know that you're not going to get those last two lines. In fact, here's what we see. If you import dis, I love dis. This is the disassembler that comes with Python, and it's going to load the constant number one, which is one, and then it's going to return that value. End of story. Okay, that's so much for the dumbest function in the world. What about this function though, where we've replaced the word return with the word yield? So now it's def mygen, yield one, yield two, yield three. And what happens when I print this function after running? So I'm going to run the function mygen. What do I get back? And, excuse me. And it turns out that I get back a generator object, mygen at some address. What the heck? What is this? What is a generator? Yield makes the difference. Yield is all that we changed here, but it turns out to be a monumental difference. The use of yield turns a regular function into a generator function. Now, when Python compiles the function and notices the yield, it says, aha, I am going to tag it differently. I'm going to add a flag there, and I'm going to say we should treat it differently. And that treating it differently means that when we run the function, we are not going to get back the result. We're not going to get back that 1 or 2 or 3. Rather, we're going to get back a generator object. Okay, well, let's just see here how Python tags it. If you use another function here from dis called show code, you can run those at any function you want. And sort of breaks down a whole lot of the pieces of the function other than the bytecode. So it tells us here, among other things, that it's called mygen. It's in a file that I call gen3.py. It even has constants in here as none, 1, 2, and 3. That's where the 1, 2, and 3 are being stored that go along with the yield. But you can also see in the highlighted text here that it says, oh yeah, the flag for generator is turned on. So what does that mean? What do we do with it? Well, the bytecodes are radically different, right? Before we saw the bytecode was take the value, return it, take the value of 1, return it, and we're done. Instead, what we get here is load a constant. That's what we got before. Yield value, and then pop the top. So if you think of it as a stack, right? This is a stack frame for our function. So it's going to yield the value and pop it. Load 2, yield it and pop it. Load 3, yield it and pop it. And then at the end, we get to load constant none and return it. So what's really going on here? What's really going on? What is yield and how is it different from return? So basically, a generator object is an object that implements Python's iterator protocol. And it's a really simple protocol. You get the iterator of an object via iter. All right, now, in the case of some objects, you will get back a separate iterator object. So if you run iter on a string or on a list or a dictionary, you will get an iterator for that string or list or dictionary. But in the case of a generator function, or a generator object, I should say, you are going to get back the object itself. So it is its own generator. The next part of the iterator protocol is you get each succeeding value with next. So if you run next, 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 you're going to get the next thing that it has. Basically, it's going to run up into including the next yield statement. And then when finally gets to the end, when we reach the end of the function, then the generator, the function body which is being run by the generator, it raises stop iteration. So this cuts to the core of how a for loop works, right? So the first thing that happens in a for loop is Python checks, is it iterable, right? So in this case here, in this example, is ABCD iterable? Is a string iterable? The answer is yes. So then we get back its iterator, right? I mentioned before we get a string iterator back. And the for loop then says, give me your next, give me your next, give me your next. So we get A, we get B, we get C, we get D. And then when the object raises stop iteration, it's not the for loop, it's not us. It's the string or the string's iterator raises stop iteration when it gets to the end. And that's the signal telling for, hey, I'm at the end. Now you can exit the loop. So what about with our generator? Well, the same thing is going to happen more or less. The first thing is that the for loop asks, is this generator object iterable? And if so, and it is, then we're going to be asking for the next thing again and again and again and assigning it to one item. So we ask the generator for its next item, we get 1. We assign it to one item, we run print. Next thing, we get 2. Next thing, we get 3. There is no next thing, so the object raises stop iteration, and the for loop knows that's the end, it exits. This is how all for loops run, and this is how a generator can sort of slide its way in there, implementing this protocol. Now, we could do this manually. I can say G equals mygen, and I'm going to get G, right? I can check to see what G is, and it's going to be then, right, some object that we saw before. And I can even run iter on G, and we're going to see we get exactly the same object back. Now, excuse me. You might not know this, but there is an ID function in Python, and that ID function, handed to any object, returns the unique ID number of the object you've handed to it as the argument. That ID number, and so if the ID numbers of 2 objects are the same, they are the same object. Guess what? The ID is actually just the decimal version of the address in memory. And the address in memory that we see here in this object printout is actually its address. So this is its ID in hex form. So we know that because the addresses are the same, the objects are the same. And because they're the same, then we know that G returns its own iterator, or it is its own iterator. And then what about next? Well, each time we run next, we're going to get 1, then 2, then 3, then stop iteration. So next tells the generator to run up to and including the next yield statement. This can be a lot of code. This can be a little code. As soon as the generator hits yield, it returns the value and goes to sleep. And that's the key difference between a regular function and a generator function. A generator function will run, when it hits yield, returns the value and sticks around. Its stack frame sticks around. All the values, all the states stick around. Everything is around there. It just sort of went to sleep, and it's going to wait for us to address it again and say next. By contrast, of course, a regular function where it returns a value, that's done, right? It's over. The stack frame is done, right? All the information is done. The state is gone. And so this keeping of the state turns out to be a really crucial part of working with these sorts of generator functions. So here's another fun example. I often joke with my classes when I teach them about generators that, I'm sure you use Fibonacci sequences all the time at work. And so this is probably like a core part of your job, right? So how's this going to work? We can have a generator that generates the Fibonacci sequence. And here, of course, the sequence is infinitely large, but we can describe it with our generator function and then just get it out one piece at a time. So first is going to be equal to 0, second is 1, and then while true, so I'm going to have this nice infinite loop, yield first, and then I'm going to use tuple unpacking to say first second equals second plus first, second and first second, first plus second. So I create the generator, I run fib, and I do next and next and next, and I can go again and again and again. So it would be really stupid, of course, to do list of fib, because what's going to happen then? List is going to say, oh, I'll just run and get a stop iteration. But of course, this is an infinite series, so you're never going to get a stop iteration, and so bad news for your computer. This is a fantastic thing to run on your colleague's or friend's computer if you don't want them to be your colleague or friend much longer. However, don't do it on your own computer. I have on some occasions, and it's very embarrassing. Okay, so here's another example. So read n. So you might know that running through a file, so file objects are iterators, right? So I can always say, give me your next, give me your next, give me your next. It's going to give me the next line one at a time. But there are many file formats that don't actually lend themselves to one line at a time. There are multiple lines at a time. So this is a generator that I call read n. It takes a file name and n, a number. And first it opens the file, and then what it's going to do is it's going to run through the file, and it's going to read n lines, and then it's going to output that. It's going to output a string. So what's it going to do? It's going to read, let's say n is 3. It's going to return a string containing 3 lines and output that again and again and again. By the way, the fact that I'm using f.readLine here means that I might get an empty string if I'm at the end of the file, which means that the last chunk that we get back might contain fewer than n lines. So this is a really useful kind of generator function where instead of iterating through a file one line at a time, I can iterate through any number of lines at a time depending on the file format. Fantastic. Here's another example that's perhaps, again, not so practical, but you can think about it, how it could be used. Get vowels. So I'm going to iterate over my file one line at a time. So that's an iterator. But then I'm going to iterate over the string, over the current line, one character at a time. And then I say, oh, if this is a EIOU, if this is a vowel, then yield it. What happens if it's not? Then we go back to the next one, the next one, the next one. So what we're going to do is we're going to have this entire file, but we're only going to get the vowels from it, EIOU. Everything else is going to be ignored because, again, we're only going to run yield if it's a vowel. And until you run yield, it keeps running. And when it hits yield, then it goes to sleep. So when do we use generators? Typically when we have a large or infinite set of values to return. When it's easy to express the idea of a function, you can implement the iterator protocol on a class, of course. But that's if you want to add the iterator protocol to an existing class. Here we're just talking about functionality that sort of makes sense standalone. So maybe we don't want to set things up like a network connection or a file, something having to do with file there, where there's such overhead. We want to start it up and then we'll just get, next. Also, this fact that we can keep state across runs and local variables is really, really useful. So what about this thing here? So here I'm going to say def mygen, all right, another generator, x equals none. And then I have another infinite loop, while true. But then I have this weird thing here, x equals yield x, and then x times equals 5. Now, before we saw that, I could say yield x. That would have been normal. But here, I'm not using yield as a statement that I want to sort of do a mini return. Rather, what I want to do here is I want to do this mini return. And that's going to go to sleep. But it's going to go to sleep on the right side of the assignment. Remember that assignment is always right side before left side. So the right side runs, yield x, we get our value back. It stays there until what? Until we send it a value. This is two-way communication, because now yield, being on the right side of the value, is going to wait for us to send it something. And then whatever we send it replaces that yield, often an assignment. It'll be assigned to X, and then it'll continue. We can do this with, indeed, the send method. Now, normally we use next. Right now, I should even say, normally we don't say next at all. Normally, we let the for loop do this nexting for us. But in this particular case, we have to do it ourselves, right? Because like we're going to be really doing things manually. So I can say next, and that's sort of like saying, go to the next thing. But if I want to provide it with a value, I need to use the send method on the generator. And if you want, you can just say g.send of none, and that's the same as saying next of g. There's no difference between the two. So now how's this going to work? Well, given my generator function, I'm first going to do g equals my gen. So I get that generator back. And then I say next of g. And this is an important point. You always need to what's known as prime it. You need to say, go up to and including that first yield where we're going to get a value back. Because before I can send it values, it needs to be on the right side of that assignment. So what's going to happen is when I say next of g, it's going to get to that yield. It's going to return the value of x, which is currently none. And then it's going to wait for me to send it something. So if I send it 10, what happens? We then have x equals 10. And then x times equals 5, so x becomes 50. We go back into the top of the while loop, and then we get back 50, and then it waits again. So now I send it 23. X is 23. We multiply it by 5, which is 115. We go back to the top, yield x, which you got 115 back. It waits. I send it ABC. It sends me back 5 times ABC. You know, ABC, ABC, ABC. And then I get it back. I send it 1, 2, 3, and I get back 1, 2, 3 times 5. So really, basically, I can send it anything that can be multiplied. And as with all functions, as with all data in Python, it's, it might be strictly typed, strongly typed, I should say, but it'll allow me to use the dynamic typing as well. So this is kind of nice. I can have my generator here waiting for me to send it something. This is known as a coroutine. All right. And a coroutine, think about it. It's a generator. It waits to get input from someone else. And the data is received with yield, usually on the right side of assignment. And the local state is still going to stick around. And I can then have this routine, and I can use it often, or I can use it rarely. It is sitting around in memory, waiting for me to use it, waiting for me to send it a message. Waiting patiently, I should add. Now, we can actually, as a Python 3.8, even cut down on what we're sending here and make our generator function even smaller. And this is using the walrus operator, as it's known, the assignment expression operator. It was so controversial. Oh my goodness, right? And this is the classic place where it would be used. It would be used in a while loop, because normally, if you're coming from a C background, well, if you're coming from a C background, I'm so sorry, but hopefully you've seen the light. But if you're coming from a C background, then typically you're going to say, oh, I'm just going to do while x equals something, something. But you can't do that in Python. Regular assignment is not considered an expression, and so it cannot be used on the inside of the while loop. But the assignment expression can be, the walrus can be. So here we're saying I'm going to get from yield, get from yield, get from yield, get from yield. And when I get an empty value of some sort, not just none, not just false, but an empty string, empty list, then we'll exit. And so this is just a shorter way to write what I did before. Now, what if you don't want to prime your coroutine? So David Beasley, who talked a lot about this, I guess it would be now 11 years ago, he suggested using a decorator. The decorator automatically runs next, gets the coroutine primed, and you just need to run send on it. So you can get around the priming if you really, really want to. I don't know if that's necessarily something you'd want to do, but you can. So what? So what now? Is this just a solution looking for a problem? Is this a cool technical hack that people will occasionally use? Yeah, largely. But so I've been trying to always think of how can people use this? Why were people so excited about coroutines, and how can we maybe incorporate into what we do nowadays? So what I'm going to try to do now is, now that I've sort of introduced the topic, how can we use them? What can we do with them? So my description is to call them nanoservices, right? Now, I haven't really heard other people talk about this. So you can either love the fact that I've come up with this name or hate it and blame me. Either way, I'm to blame, or to be credited. In any event, many systems nowadays use what are called microservice architectures. And the idea is let's have many, many, many little services running on many, many, many little computers, typically nowadays in the cloud, but they don't have to be. And so if I need to do authentication, I'll hit that microservice. I have to get location, I'll hit that microservice. And what you have then is instead of one big web service doing lots of stuff, many little services doing little things, each on its different service, and each has its own API. So I've come to think of coroutines as in-memory nanoservices. They're even tinier than microservices, right? They're teensy-weensy. They fit into memory. They're inside of our process, even inside of our thread, right? But there's no overhead. You don't have the network or objects or threads or processes overhead. They're right there. It's a function call, and we do function calls all the time, and those are really well optimized in Python, but they have their own state. Now, you will need to come up with your own protocol for coroutine, but you can use all of Python's data structures as we saw just now. I can use send with anything I want. So how can I do this? So here's one example. I can use MD5. So MD5 is a popular hash function you can get through hashlib, and it's a real pain to use in Python. All right, so let's create a little coroutine that'll provide MD5 as a service. And MD5AAS. I'm sure they're gonna, the kids doing starts will call it. So I can say import hashlib, def MD5 gen. So this is my MD5 generator, and it's a coroutine. So it's going to get something from me, and then it's going to go through the create MD5, and then encode it, and then do a hex digest. So it's going to output something, and I can just keep sending it more and more and more, and it'll keep doing MD5, MD5, MD5. Here's another one. I can get the weather, right? Everyone cares about weather, especially when you go outside. And so basically, I can say here import requests. And I actually found I think it's the World Weather Service. I can't remember what it's called. What World Meteorological Organization? I looked it up. I found it. Any event. So you can run a quick weather retrieval system using a simple URL. So you can basically say, okay, well, HTTPS World Weather WMO int JSON, and I want to get the JSON for a particular city. So if I send a request for a particular city, and the cities are all numbered, it will give me back some information. Right, and here, look at this. I'm then going to iterate over that for one forecast in weather, city, forecast day, give you one forecast, one forecast, one forecast. So if I do g equals that, and you can see here how my generator function, my coroutine can take an argument. Then I say next, 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 and each time I say next, it's going to give me the weather, then the next weather report. So I had for July 31st, then for August 1st, then for August 2nd. And you might be saying, wait, that's not a coroutine. Well, no, because I was using next there. So let's try something else. Here's my coroutine example 2.1 for the weather. I'm going to say get forecast. I'm going to say next. That's priming it, right? And then it's going to say, oh, send me a city number or none. Well, if I send it none, what's going to happen? The while loop is going to get effectively a false statement in Boolean context and exit out of the while loop. But if I send it a number, then it's going to go do the request, then yield. I'm going to keep getting it. And we can keep going. And then when it gets to the end, it's going to send me city number or none. So I can keep going and get different cities' weather forecasts. I have a little weather service running as a coroutine. Pretty snazzy, huh? Here's another thing I can do. I set up a little database containing my kids' information here, and using PostgreSQL. And so I've set up what I call the People API coroutine. So now I connect, and remember, database connections can be expensive. I can then say, okay, let's get a query. And I'm going to get a query I'm going to get it from the D : equals yield output. So we're going to put it into D there. And then I'm going to look for which field we want and what value we want for it. And so we're going to fetch then all of them. Meaning I have a little database wrapper here. It's not quite, I can't remember what's called right now. It's not quite the ORM, but it's a simple ORM. So I can now say G equals People API, then next. So that's going to prime it. And then I'm going to send it a dictionary. I'm going to say, I want to look for anyone with the last name of Lerner. Oh, and I get one result back. And then I can send it something, and it'll say, okay, send another query. I can say, well, how about Lerner Free, which are my 3 children's last names? So then we get 1, 2, 3 back, and then it says send a query or done to quit. So meaning basically, I can just keep asking and do different queries against my database. So how can I tell this generator I'm completely done? Well, one is we saw I can just send it none. But I can actually use the close method, right? I can basically say g.close, and that exits from the generator without using stop iteration. Now, if you try to use it after closing it, you'll get a stop iteration exception. But what if I want to exit from the current query, keeping the generator around? Like I want to sort of exit from it and then come back and try it again. What if I could send the generator a signal, right? And now what kind of signal can I send? I can use the throw method. We can raise an exception using throw. And normally if I use raise means I want to raise the exception right here, right now from where I am. Throw means I want to make sure the exception is actually happening from inside of the generator, from inside the coroutine, from the point that it's currently at, from the yield. Now, people often are like, wait a second, exceptions are errors. No, they're not. Absolutely not. In fact, we saw this earlier, right? Stop iteration. Stop iteration is not an error. It just means we are at the end of the iteration. In the same way, then, we can use this as a primitive communications mechanism inside of our thing. So what I can do here is I can say, look at this. Here's my get forecasts. And I can put inside of the getting each forecast, try, except different city exception. So what I can do now is I can say, give me the forecast. Next. Okay, so we got a private. Give me city 44. Give me city 44. Oh, and then I'm going to throw a different city exception. I don't then need to go through the entire sequence. I can just say right now, right here, I want to go back to the main menu. And then I can go and send it 49. And then again and again and again. So our Nanoservice is a simple request and response interface. It uses Python data structures, and it keeps state across the invocations. And it even can cache data, right? So what we saw before with the weather is we got a whole list, but we only were spoon feeding out one little bit at a time. Now, what if I want to have lots of functionality in our coroutine, right? So imagine I want to combine the MD5 service and the weather service. I know, not the best idea, but mergers are all the rage nowadays, and sometimes companies that shouldn't are merging together. So I'm going to pretend that the MD5 corporation and the weather corporation are joining themselves together. They'll make a hash of the weather. Okay. Anyway, so now what I can do is I can say, we're going to have our different city exception. We're going to have our combined generator. And look at the first part. We're going to say if s equals 1. So I'm going to say send 1 for weather, 2 for MD5, or none to exit. Right? It's like a phone system, like an operator. So if s is 1, then we're going to go through our whole city generator. If s is 2, we're going to go through our MD5 generator. Now it does work, right? I can now do send 1, send 44, so I'm going to get the weather, throw a different city exception, get a different one, but then I can go back, send none, and I can ask for MD5. All of that is working great. But as I like to say, unfortunately this works. This code means that my generator has become big, really big. If you had a regular function that did this, you'd be really upset. Right? What you would do is you'd break it apart into smaller functions. So what I really want to do is have smaller generators. Here's what I'm going to do. I'm going to have my combined generator, but I'm going to change it. Now, if s equals 1, just call the city generator. And if s equals 2, call the MD5 generator. Then I can have my original older generators there factored out. The problem is it doesn't work, right? Other than that, we're doing great. So the problem is I do a next, I do a send, and it's like very confused. It doesn't quite know what to do. And that's because these are separate layers of generators. Our combined generator is just a regular function. It's not yielding anything. So maybe we could just iterate over the items that the generator returns. Well, that's not going to be enough because we're sending to the outside generator, but we need to send that message to the inside generator. That's where we come to yield from. Yield from lets us have a generator that then offloads things to sub-generators. So if you want to have this combined generator, you'd say yield from, go to the inside one, and all the communication then goes sort of through our combined generator. So if you do a throw, if you do a close, if you do a send, it goes from the outside directly into the city generator or into the MD5 generator, and the combined generator is just a conduit. Right? So sending from the outer is past the inner, from the inner is past the outer. Exceptions work, close works. Yield from is made for sub-coroutines, which I'll tell you, not a lot of people know. Everyone's like, what is yield from for? Oh, it's so that you can do yield instead of a loop. Really? I don't think that's the only reason it's there. And as we see, it's not. And so sure enough, I can now run my combined generator. I can get some MD5 stuff. I can go back by sending none. I can now send some weather stuff. I can throw the exception. All is good. Now, I promise you that I'd say a little bit about async IO. The fact is, what is async IO? Async IO assumes that I'm going to have this loop around and around and around running some coroutines. Well, early versions of async IO actually use generator functions. Why? Because they can be stopped and started. This is effectively what's known as cooperative multitasking, an earlier form of multitasking that in many ways, the reason, oops, sorry, let me just dismiss that. In many ways, because it was so much easier to work with, was very common in sort of older operating systems, old versions of the Mac, old versions of Windows. The good news is it's easy to work with. The bad news is that if you have a badly behaved coroutine, then the whole thing goes to pot. So modern asyncio doesn't use generate function. It uses special keywords, async def and await. The ideas are similar though. So if you like this idea of I'm going to wait for it, I'm going to go to sleep, that's sort of kind of like what await is doing. It says I know this thing is going to take a long time, so I'm going to return control to the loop. So don't be confused, but at the same time, you can use this like a handhold to getting into the asyncio. So should you use coroutines? They can be really useful. They can be very powerful. It's in memory. You can set up the API. You can deal with large amounts of data, but one chunk at a time. And you can even have these sub generators with yield from. But I am warning you, these are not so well understood. It might seem weird to use send in this way. You might want to wrap it up. And when things go wrong, and they will, debugging can be a little difficult. Anyway, if you have questions, I have a few minutes. I'm sorry, I'm like on a crazy schedule. I would be delighted to answer questions. Thank you so much for your participation and for the lovely emojis and reactions. And I'm really, really delighted to be here at a part of your conference.
Thanks a lot, Reuven. Feel free to ask any questions in the Q&A section and raise your hands if you want to speak with Reuven on the stage. I have a question though. So, how effective is to pass around these generator objects or generator functions using pickle around in the network? Do you think that's a good idea?
Ooh. So, first of all, can you pickle functions? I'm not sure. I'm not 100% sure. I think so. I know you can pickle just about anything
They're
in
objects,
Python.
right? They're objects.
Yeah, but there are some objects you can't pickle. I'm going to guess you can. I'm going to guess you can. Oh, you can pick. I know you can pickle objects. I'm not sure if you can pickle function objects. Oh, generator objects. Oh, right, of course. It's generator objects, no longer function. So even if that were a problem, um, yeah, that could definitely work. I would say you want to be a little careful with that because passing code around like can be a little dangerous. And I once talked about using pickle, and boy, someone really read me the riot act. He was like, "Pickle is not secure." But if you're in your own little closed system, oh my god. Anyway, if you're in your own little closed system, that could work. That could work pretty well. I know of at least one place where they actually do store like functions in pickled form. Now that I think about it, and they retrieve them and they use them in their system. I don't know if I'm trying to think though. If you pickle a generator, it keeps its state. Wow, I hadn't thought about this at all. Wow, this is like opening up new ideas here, where you can like have it freeze it. It's like not even going to sleep. It's going to like winter hibernation, and then you can like thaw it out using
Because
pickle,
you're
and then keep going.
you're essentially sort of passing around workers. If that makes any sense, you're just passing around workers. Because these generator objects or functions are basically workers with statefulness embedded into them, and that would really be interesting, right? I mean,
I love that. Oh, that is so fantastic.
yeah.
Great point. Oh, now I've got to like experiment with that.
If you have any questions, please post them in the Q&A section. I think we have 2 minutes. I think the next session will be probably starting in another 7 minutes. So, Reuven, thanks a lot for this session. It was really insightful. Hopefully, next year, when the pandemic is done, we could meet in person in the next PyConf Hyderabad.
I look forward to it very, very much. I'd be delighted to come in person. Thanks,
Perfect.
everyone. Have a
Thanks a lot.
fantastic rest of the conference.
Thank
All the
you.
best. Bye, folks.